All right, for part C, this is where we can start the examples finally. In this case, I've chosen to work an example that was sort of set out for you in the textbook, but they didn't show you how to get to the final answer. And I want to point out, actually, as long as we're here, that the introduction to this question down at the bottom of one of those example boxes, it says that chlorine reacts with hydroxide ion to form chloride ion and perchlorate ion. And I was kind of scratching my head trying to figure out how that could possibly work out. This is why you see all the scribbles out here. And then I noticed that they give the answer down at the bottom of the example box, but they don't show you how to get it. And well, in the answer, it's the chlorate ion, not the perchlorate ion. So that was a mistake. It's chlorate ion. It's ClO3 minus that it's actually going to. And that actually worked out. So they didn't give the charges originally. They just gave the description, chlorine, the element, and hydroxide ion will react to form chloride ion and perchlorate, or sorry, chlorate, I almost made the same mistake, chlorate ion, ClO3 minus. And you have to make sure that it's balanced, and actually it is balanced with all the coefficients being 1. And then you have to find out what the oxidation states are. For a redox reaction, that's something important that you really have to know. It's interesting here that if you find out all of the oxidation states, it's the chlorine, the Cl2, that's being oxidized and reduced. And that may seem weird, and it is kind of weird. It's unusual, but it can happen if you have more than one atom of the substance. Then it's possible that one atom of it is being oxidized and the other atom is being reduced. And so if for both of the half reactions, you start out with a chlorine atom with 0 charge. Actually, I corrected myself. The equation is not balanced. I said balance it. Balancing this equation is the entire point of what we're doing. So actually, it's not balanced to begin with. But we do need to find the oxidation states. So for the reduction, we have chlorine with 0 charge going to chloride, Cl minus, so 0 to -1, that's a reduction. And then the other atom of chlorine goes from chlorine with 0 charge to Cl plus 5, which is the charge of chlorine in the chlorate ion. And we saw that, we worked out that example a few minutes ago, so I'm not going to show it again. You can look back at that if you want to see how we arrived at that conclusion. But anyway, it's plus 5. Okay, oops. Right, okay, so, right, plus 5. And that's the oxidation. So for the half reactions, we have Cl2, because that's the compound in which the atoms being reduced and oxidized are found. You'd write the formula for the entire compound, not just one of the atoms. So Cl2 with 0 charge goes to Cl minus with a -1 charge. Don't worry about balancing the chlorines yet. We'll do that later. And Cl2 with 0 charge goes to ClO3 minus. And again, don't worry about balancing the chlorines. We'll do that later. In step 2 is where we're going to do it, actually. The step 2 says balance all of the elements except hydrogen and oxygen. So that means that Cl2 here has to go to 2 Cl minus on the product side. And Cl2 here has to go to 2 ClO3s on the product side. Then in number 3, we balance excess oxygens with H2Os on the opposite side. So in the first, the reduction half reaction, it's actually okay. There are no oxygens. For the second oxidation half reaction, we have, we start out with just chlorine on the left-hand side and 2 ClO3s on the right-hand side. So on the right-hand side, we have 2 times 3 or 6 oxygens that we need to balance. That means we need 6 more oxygens on the left-hand side, and we get those by putting in 6 H2Os. We added some hydrogens too, but we'll fix that in the next step. So now the chlorines and the oxygens should balance from one side to the other. Okay, the next step is where we balance excess hydrogens by adding H plus to the opposite side. Again, the reduction half reaction is okay the way it is. There are no hydrogens. But the oxidation half reaction has 6 times 2 or 12 hydrogens on the left-hand side. So we add 12 H plus on the right-hand side. So now we have 12 hydrogens on the left-hand side, 12 hydrogens on the right-hand side. Now we balance the charges by adding electrons to whichever side has the more positive charge. So where we stand in the last step is Cl2 going to 2Cl minus. For that, we've got a total charge of 0 on the left-hand side and a total charge of -2 on the right-hand side. And if adding electrons is the only way you can balance that charge out, that means you have to add the electrons to the side with the more positive charge, which in this case would be 0, because versus -2, 0 is more positive. So you'd have to have 2 electrons on the left-hand side. Okay, so this is the finished version. Now for the oxidation half reaction, we've got a total charge of 0 on the left-hand side and a total charge of, let's see, -2 plus 12. Overall, that's plus 10 on the, plus 10 on the right-hand side. And that means in order to get it to balance out with the 0 on the other side, we're going to have to add 10 electrons to the right-hand side. So now we have -2 plus 12. That gives us plus 10. And the 10 electrons give us -10. And that brings it back down to 0. So 0 on the left, 0 on the right. So the charges are now balanced from the left to right hand side on each of the oxidation reduction half reactions. Then, this is just a copy of where we were in the last step, just so we won't forget. And then number 6 is make the number of electrons equal. You'll notice here in the reduction half reaction, we've only got 2 electrons that are being taken in by chlorine, but in the oxidation half reaction, we have 10 electrons being released by the chlorine. And you can't have that happen. If you only need to take in 2 electrons, you're not going to release 10. Those other 8 electrons have to go somewhere. So what we do is we make the 2 equal. We've got 10 here and 2 here. So the simplest way to do that would be to multiply the entire first reduction equation by 5. So that's what we'd do. Multiply all of the coefficients in the reduction half reaction by 5. So it becomes 5Cl2 plus 10 electrons goes to 10 Cl minus. When I found out what the product really was, the number of electrons changed. Okay, so the oxidation half reaction stays the same because it already had 10 electrons. So now we've got the same number of electrons coming as we have going, and that's good because, again, they have to be equal because they're the same electrons. And then in the next step, we add the balanced half reactions together. In order to do that, what we do is we essentially add up everything on the left-hand side and write it out. And then we add up everything on the right-hand side and write it out. So we're essentially splitting the reaction at the arrow. So adding it all up, we have 5Cl2 plus another Cl2 from the oxidation half reaction, plus 10 electrons, plus 6 H2Os. And that's everything on the left-hand side of the arrow. For the right-hand side, we have 10 Cl minus, plus 2 ClO3 minuses, plus 12H plus 10 electrons. That's everything on the right-hand side of the equation. of course, we can combine the 5 Cl2s with the 1 Cl2, and that gives us 6 Cl2s. And you'll notice that there are 10 electrons on both sides of the equation, so they cancel out, so they won't appear. And that's essentially all we have. So this is your balanced overall reaction, but there's still one problem. It said in the question that this is in a basic solution. You can't have free H plus ions floating around in a basic solution. So we have to take care of that. If we've got 12 H plus ions on one side or the other of the reaction, what that means is we have to add 12 OH minus ions to both sides. Okay, because 12 OH minus plus 12 H plus yields 12 H2Os on the side that has the H pluses. On the other side, you just have 12 OH minuses hanging around, but that's okay because it's in a basic solution. So we end up with 6 Cl2s plus 6 H2O plus 12 OH minus yields 10 Cl minuses plus 2 ClO3 minuses plus 12 H plus 12 OH minus, which is 12 H2O. So here's the equation with the H pluses and OH minuses combined into H2Os. And this is your overall balanced equation in a basic solution. But there's still one more thing, well, a couple more things you can do. We've got H2Os on both sides of the equations. You've got 6 on the left and 12 on the right. So essentially what that means is that you can cancel out 6 of them. All 6 on the left and 6 of the 12 on the right. All right, so you end up with 6 Cl2s plus 12 OH minuses yield 10 Cl minuses plus 2 ClO3 minuses plus 6 H2Os. One last thing you should do is make sure that you have the lowest whole number ratios for everything. And you can do that by looking at the coefficients. 6, 12, 10, 2, and 6 can all be divided by 2. So you do that. That's the largest factor that they can be divided by those. So you do that, and you end up with 3 Cl2 plus 6 OH minuses yield 10 Cl minuses plus 2 ClO3 plus 6 H2O. And that will be all balanced. I actually checked for balance before I divided by 2, but you can see everything balances out. Only it would be 6 and 6 and 6 and 6 and 6 and everything down the line after dividing by 2. And the charge balances also. We have 6 negative 1s for a charge of negative 6 on the left-hand side, and on the right-hand side, we have, hang on, 10 Cl minus plus 2 Cl, no, that's still, yeah, because I didn't divide those by 2. Huh. Okay, that was silly. 5 Cl minuses plus 1 ClO3 plus 3 H2Os. Now everything should balance because I only divided by 2 on the left-hand side for some reason. And that's why it's a good idea to check at the very end once again. So we have negative 6 as the total charge on the left, and we have negative 5 plus negative 1 for a total of negative 6 on the right-hand side. So now it is finally balanced. And that is the answer that they give you in the textbook at the bottom of the little box there. All right. Our next section is, and we still have time to go, so I'm going to keep going. We finally get out of section 2 and get into section 3. Section 3 is about reaction stoichiometry. That's how that weird word is pronounced, or actually stoichiometry, I guess is technically how it should be said, but it's stoichiometry is close enough. Stoichiometry has to do with the amounts of things that are involved in chemical reactions. And the reason that we balance chemical reactions by putting coefficients in them is so that we are able to relate amounts of one thing to the amount of another thing involved in a chemical reaction. And that's essentially what stoichiometry is all about. If we want to produce this much product, how much reactants do we need to put in? That's stoichiometry. And in order to accomplish things like that, we use the coefficients from the balanced equation. All right, and the coefficients in the balanced equation allow us to relate exact quantities of one thing to exact quantities of another thing in a balanced equation in terms of either atoms and molecules or groups of atoms and molecules. The most convenient way would be to use moles of one thing versus moles of another. It is important to remember, though, that you can't use the stoichiometry directly with masses of one thing versus masses of another. There are extra steps required when you're dealing with masses. Okay. So this equation here, 2H2 plus O2 yields 2H2O, tells us that if we have two molecules of hydrogen and one molecule of oxygen, we can combine them together to form two molecules of H2O. It also tells us that if we have two groups of hydrogen atoms, say moles perhaps, 2 moles of hydrogen will combine with 1 mole of oxygen to yield 2 moles of H2O. But you don't necessarily have to have those exact numbers of moles of hydrogen and oxygen. You can have whatever number of hydrogens or oxygens you have, and the real advantage to the coefficients in the balanced equation is that they give you ratios of how things relate to each other. So you can also look at this equation and say, however many moles of H2 you have, you only need half as many moles of O2 because the ratio is 1 to 2. You need 1 oxygen for every 2 hydrogens. And it works that way with moles too. You need 1 mole of oxygen for every 2 moles of hydrogen, but you don't necessarily have to have exactly 2 moles of hydrogen. So if you have, say, 3 moles of hydrogen, you need half as many moles of oxygen, or in other words, 1.5, because the ratio of, say, 3 versus 1.5 is the same as 2 to 1. If you want to produce a certain number of H2Os, then you're going to need the same number of H2s because that's a 2 to 2 ratio, or in other words, 1 to 1. But you're only going to need half as many O2s because that's a 1 to 2 ratio. So what we really do with these coefficients once we balance the equation is we use them as ratios to figure out how the quantities of one thing relates to quantities of other things in the reaction. Just as an example, using the above equation, which I'm going to write again here. And the way we use those ratios is basically you take what you're given or what you're starting out with, and we do it like a unit conversion. You take the amount in number of atoms or molecules or moles of atoms or molecules, and you multiply it by the coefficient for what you want to go to divided by what you're coming from. So in this equation here, if you have 8 moles of hydrogen, how many moles of oxygen do you need? That's pretty easy. You need half as many, so it's 4. But to set it up formally, because not all of the numbers will be that easy, you would take what you're being asked about or what you're given, which is 8 moles of hydrogen, and you multiply it by the coefficient for what you're going to, divided by the coefficient of what you're coming from. So you want to relate moles of hydrogen to moles of oxygen. So that would be the coefficient from oxygen, which is 1, over the coefficient from hydrogen, which is 2. And notice how the units cancel out. Moles of hydrogen cancel with moles of hydrogen, and the unit left over would be moles of oxygen, which is what you're looking for. And the number would be 8 times 1 divided by 2, which is 4. So to use numbers that maybe aren't quite so obvious, if I want to produce 7.86 moles of H2O, how many moles of hydrogen do I need? Well, actually, this is pretty obvious because it's going to be the same. It's a 2 to 2 ratio. 7.86 moles of H2O times the coefficient of what you're going to, which is 2 moles of H2O. Sorry. 2 moles of H2 is what you're going to. So 2 moles of H2 for every 2 moles of H2O. Moles of H2O will cancel out, and moles of H2 will be the unit for the answer, which is what you want. And the number will be 7.86 times 2 divided by 2, which is 7.86. So it is the same. How many moles of oxygen would be required to produce 7.86 moles of H2O? Okay, well, 7.86 moles of H2O times the fact that you only need 1 mole of O2 for every 2 moles of H2O produced. Moles of H2O will cancel as a unit, leaving you with moles of O2. The number would be 7.86 times 1 divided by 2, which is 3.93. So that's how many moles of oxygen you would need if you wanted to produce 7.86 moles of H2O. If you're having trouble grasping how these things relate to each other, it can be helpful to make an analogy to baking, like a recipe where you have so much of this, so many cups of flour plus so many cups of sugar plus this number of sticks of butter, and so on, will combine to bake this many cookies. And so if you want to have this number of cookies instead, how many cups of sugar do you need? And it's essentially the same idea as this. And the book goes over it on page 197. That's in the hard copy of the book. It would be 207, I believe, in the PDF. And so you can look that over if you're having trouble grasping what's going on here. That might make it a little more understandable. And I just wanted to remind us again that stoichiometric ratios can't be used directly with masses, only with number of molecules or groups of molecules, like for instance, moles of molecules. If you want to do it with masses, then there are extra steps involved, which we will get to in a little while. So an example of something like this might be a little more, something a little more complicated might be what number of molecules of ammonia can be produced by a reaction of 4 moles of calcium hydroxide, according to the reaction above, assuming that you have enough of the other reactant. And we'll see in a little while what happens if you don't have enough of the other reactant. But anyway, if they don't tell you how much of the other reactant you have, then you pretty much have to assume that you have enough. All right, so we know that we're putting in 4 moles of calcium hydroxide, so that's what you start with. And look at the equation. You get 2 moles of NH3 for every 1 mole of calcium hydroxide. So it's 2 moles of NH3, what you're going to, divided by 1 mole of calcium hydroxide, which is what you're coming from. Moles of calcium hydroxide will cancel, and you get 8 moles of ammonia. But the question was actually how many molecules of NH3. So whenever you're doing stoichiometric problems, you always have to go by way of moles. And then before using moles and after using moles, you can use any other units that might be involved. Like in this case, we started out with moles of calcium hydroxide. So the first thing we want to do is convert the moles of ammonia. And then to get the molecules of ammonia, you would take the moles times the number of items in a mole. So it's 8 moles of ammonia times 6.022 times 10 to the 23rd. Remember Avogadro's number? There it is again. NH3 molecules per mole of NH3. And notice moles of NH3 cancel out, and you get molecules of NH3 as the unit. And the number would be 8 times 6.022 times 10 to the 23rd divided by 1 if you really want to do that. And it's 4.8 times 10 to the 24th. So it's a very, very large number. Okay, then when masses are involved, we often do problems like this with masses because masses are easier to measure in the laboratory, but it does make the calculation a little bit harder when you're using stoichiometry. So essentially what you end up having to do is, again, you have to go by way of moles. So if you're starting with a mass and you want to find a mass, what you're going to have to do is get from the mass of the thing you're starting with to the moles of that substance. And then you can convert to the moles of the other substance using the balanced equation. Then you can get to the mass of the other substance. So like if you want to go from mass of substance A to mass of substance B in a balanced equation, then what you're going to have to do is go first from mass of substance A to moles of A. And to do that, you use the molecular weight of A. Then you can go to moles of B using the stoichiometric ratios. Then from moles of B, you would go to mass of B using the molecular weight of B. And we'll see how to do that in detail next time, but for now, we're out of time. So I'll see you then.